Welcome to this brief presentation about my research on autonomous soaring with end-to-end reinforcement learning at the University of Stuttgart in 2022. First, I would like to answer the question, why are we conducting this research? Our motivation is rooted in the limited endurance of electric UAVs due to their high energy consumption. In the case of fixed-wing aircraft, the endurance can be significantly improved by exploiting energy from updrafts, as has been demonstrated by glider pilots for decades. Therefore, we want to enable UAVs to perform energy-efficient cross-country soaring as well. However, this poses a complex problem. Not only are updrafts hard to model dynamic phenomena, but the UAV also needs to trade off the action of tracking the path against gaining height by exploiting known updrafts and localizing new ones. Hence, we develop an end-to-end model-free deep reinforcement learning approach, since this provides us with a systematic framework for learning such long-term correlated decision-making tasks by directly interacting with the complex environment. In 2022, we made great progress towards autonomous cross-country soaring by successfully demonstrating an autonomous updraft localization and exploitation. To achieve this, the following reinforcement learning approach has been developed at the Institute. The agent takes its position and climb rate as observations, processes them in a deep policy network which contains an LSTM cell to capture dynamics, and eventually outputs bank angle commands to control the fixed-wing UAV in the environment. In return, the agent receives the integrated climb rate as a reward signal. This directs the learning process towards a policy which aims at gaining as much height as possible. First, we have used this approach to train an agent in simulations. The plots of the learned behavior show that the agent performs some exploratory soaring until an updraft is reached. Then, the agent gains height by circling and tracking the updraft center, which drifts due to wind. In fall, we validated the approach in flight experiments with an autonomous glider aircraft, where we could observe the same successful behavior. We accomplished this sim-to-real transfer by directly running the policy learned in simulations in real time on board, indicating the robustness and low computational demand of our approach. This was an important milestone on the roadmap towards autonomous cross-country soaring, but we are not there yet. For cross-country soaring, we need to combine updraft localization and exploitation with path tracking. This poses new requirements on the underlying model architecture's abilities to process long-term correlations. For instance, it should then ideally be able to remember the location of previously detected updrafts. For this reason, we are currently investigating the applicability of architectures based on transformers, temporal convolutional neural networks, memory-augmented neural networks, and LSTM variants to long-term correlated decision-making in a reinforcement learning setting. Thank you for listening, and I also want to thank my colleague Stefan Notter, who has developed the updraft localization and exploitation approach, as well as my supervisors Professor Walter Fichter and Junior Professor Amir Ahmad. Please contact us if you have any questions.